This is level 2 of the CFA program, the topic on fixed income and the reading on the Arbitrage-Free Valuation Framework. Let me just quickly remind you about this concept of arbitrage. Simply means that no investment is required, no risk is taken, yet a positive return is realized. Now, this notion of an arbitrage-free valuation has been around for a really long time. It's filled with common sense. And in addition to being based on common sense, it's really well established and well known. What we're going to do inside of this reading is we're going to look at a framework. I want you to think of this as, kind of a big picture, a frame under which we're going to value a bond. And we're going to start with the market price of the bond, and then we're going to compute the present value of those promised payments. Now, you might be thinking along the following lines. You might say something like, Jim, we used this financial calculator back in level 1, and we just used our 5 time value of money buttons to compute the price of a bond. And of course, we did do that, and that was an estimate of a bond price. But remember that in our previous reading, we talked about this idea that yield curves are not flat. And sometimes even when they are flat, they never stay flat. So we're faced with upward or downward sloping yield curves, which means we have spot rates that change and then forward rates that change. And so the idea of computing the price of this bond based on one interest rate, when you put one I in there, didn't we talk just recently about the problems with using yield to maturity as an input to discount and value a price of a bond? So what we need to do is come up with a framework in order to use this well-established arbitrage-free notion to be able to compute the market price of a bond. It's really fascinating stuff. What we're going to do is we're going to rely on what's known as an interest rate tree. And you'll see this as we go through the learning outcome statements. What I'm going to do is call your attention to the second one. Calculate the arbitrage-free value of an option-free fixed-rate coupon bond. That's the LOS that you need to focus on inside of this reading, because in order for you to calculate this option-free value, you're going to need a binomial interest rate tree, you're going to need backward induction, you're going to need to understand calibration, and then of course that's going to give us an arbitrage-free valuation. And then we'll do a couple of different things at the end of this slide deck, but that second LOS is really the bulk of this reading. If you can calculate that value and understand each of the inputs, then all of the other LOSs fall in line. All right, the first LOS is a good one. Explain what is meant by arbitrage-free valuation. And we'll talk about this throughout the slide deck. Look at that first circle point. An approach that determines bond values, all right, we already talked about that, under the assumption that arbitrage opportunities do not exist. And of course, this is based on that old economics theory about the law of one price, which simply tells us that if two goods, which are pretty good substitutes for each other, they ought to sell for the same price. Of course, extending that into financial markets and financial securities, if you have two bonds and they have the same cash flows and they have the same level of default risk and interest rate risk and duration, convexity and all that stuff, well, they ought to sell for the same price. If they don't, then there would be an arbitrage opportunity. Very quickly, this is just a short part of this reading. Value additivity simply means that the value of the whole must be equal to the value of the sum of all of the components. Remember what we can do with a coupon paying bond. Let's suppose we have 5 years, and forget about semi-annual here. So we have five coupons and then the principal payment at maturity. Well, what you can do is you can strip away each of those 5 coupons, sell each one as a zero coupon bond, so to speak, and then sell the principal payment as a zero coupon bond, so to speak. So when you strip out all of that, value additivity says that those two prices ought to be the same. What's a little bit more interesting but similar is this idea of dominance. I learned this in graduate school, stochastic dominance. And that was a fun lecture that I listened to from one of my professors. But what happens is that if in fact you find a security that is cheaper based on its expected future cash flows, there's an arbitrage opportunity. Let me show you just a quick example here. Suppose we have two risk-free zero coupon bonds, A and B. All right, so A has a price of 100. B has a price of 300, and then look at those payoffs in 1 year. Clearly, they're different rates, right? You have to compound them out at a different rate. However, notice that second arrow point, since both assets are risk-free, they have the same discount factor. So the arbitrage opportunity to take advantage of this dominance, not necessarily stochastic dominance by any means, but this is just a simple example of dominance. What we could do is we could we could sell 3 units of A. That gets us $300 today. And then we could go ahead and buy 1 unit of B. And then notice what happens in the end. You know, we received 300 and we paid out 300. So there's that zero cash outlay requirement. And then all we need to do is take the 330 from B and then pay off the 315 to A. And there's at the very bottom our arbitrage profit generated. And so this idea back here of arbitrage opportunities is that if there is dominance, then you can do this. And there's probably another simple example where you could do value additivity. But in this remember, in this arbitrage-free valuation, there is no such thing as value additivity, arbitrage opportunity, or dominance arbitrage opportunity. If there were, you would do it like this. Now let's get back to this idea of stripping and reconstituting. This is what I was saying just a moment ago. What we're going to do is separate the coupons and then resell them as zero coupon bonds. Then what we can do is we can aggregate the stripped coupons and then reproduce the underlying coupon paying treasury bond. Now there's that flat yield curve that I was telling you about that hardly ever exists. And when it does, it's not going to stay like that. But here's what the reading calls the traditional method, which is what we could do using our financial calculator. All we need to do is take the present value. And there's that general formula there. So those S's, notice the S's in the denominator, they don't have any subscript because that yield curve is flat, meaning that the yield to maturity at point 1 and 2 and 3 and 10 and 20, and however far the bond matures, there's no need for a subscript, so you just compute the price of the bond like that. That's what we did in the very beginning of level 1. Then, of course, we talked about this in a recent level 2 reading, is suppose that the yield curve is not flat. Well, then we need to go to our bag of spot rates and say, okay, what's the rate for 1 year? What's the rate for 2 year? What's the rate for 3 and 5 and 10? All the way out till the bond's maturity. Note that there is a subscript under the S because we're discounting at different spot rates because the yield curve is upward sloping. And of course, this would be true if the yield curve were downward sloping. But I want you to look at that last orange arrow point. This generates an arbitrage-free value. So I think this is really the heart of what that first LOS is asking, is that what we do is that we know what those payments are going to be, right? Those coupon payments, and we know the future value of the bond. That's par value, right? 100 or 1,000, depending on what convention we're using. And then we're going to discount those at those spot rates. Probably, if this is a treasury bond, this will be the treasury spot rates. And of course, what happens then is that the right-hand side of the equal sign is equal to the left-hand side of the equal sign. And so we call that present value an arbitrage-free value. So then the question becomes, all right, what happens if that PV on the left-hand side is not equal to the market price of the bond? Well, that's where we get into the whole discussion from a previous reading in which we try to say something like it's overvalued or undervalued. However, back in this, I want to go back to those LOSs here really quickly. So look at this third one here. Describe a binomial interest rate tree framework. And there's that frame that I was talking about. And of course, the title of this reading is Arbitrage-Free Valuation Framework. So what we want to do, let me just scooch over here to where I was. There's the upward sloping. Whoops, I went one too many. The idea of this framework is that we want to put together a frame so that the right-hand side of the equal sign is going to equal to, are you ready for this? The arbitrage-free value, but it's also the market price of the bond. Here's just a super quick example. 8% semi-annual coupon bond, priced at $800, 2 years to maturity, et cetera, et cetera. So let's go ahead and compute the arbitrage-free value of the bond. We have 8% coupon, so there's the 40s in the numerator, so it's 2 years, so there should be four of those, plus the 1,000 maturity date, maturity value paid on the maturity date, and then we're just going to discount those at the spot rate. So half of 16, half of 17, half of 16, and half of 15, and that gets us to 881. So here we compute the arbitrage-free value of the bond, and that happens to be different than the price of the bond. All right, so there's our arbitrage opportunity using the spot curve. What we want to do is extend that so that the 881 turns out to not be 881, but turns out to be 800. And that's this framework that we're going to do. And here we're going to introduce this binomial interest rate tree framework. All right, so what do we know about a tree, right? A tree grows and it grows out, and there's all sorts of branches. And if you look at a big old oak tree, you'll see those branches, they're random and they go this way and that way. I guess it's depending on where the sun is. I'm not a scientist, but that makes common sense. But we're not going to put together a tree like the oak tree in our backyard. We're going to put a tree together in a framework so that it is logical. We're going to start at point A, which will probably be just the spot rate over the next period. And we're going to make the assumption that interest rates can either move this way or they can move this way. And then we're going to add branches all the way out. And we could have, so think about as we go this way, we have two possibilities at the beginning. We call those nodes. And then we have a whole bunch more and a whole bunch more. If we had, do you remember me telling you about this 1,000-year bond that was issued in the last 15 or 20 years? Boy, think about that tree. You can't even imagine how far that thing goes way out to the right. So we start here at time period 0, and we can either go this way or this way. And one of the assumptions that we're going to make is because we're relying on some type of randomness, even though the reading is quick to emphasize that this is a structured random walk, we're going to assume that 50% chance that the interest rate goes this way, 50% chance that the interest rate goes this way. So look at that third diamond point. The binomial interest rate model is a log normal random walk, and I'll tell you more about that in just a little bit. Probably some important properties down there. I would know these, but I think once we work through the examples, you'll have these three diamond points illustrated. Interest rates are going to be positive. Higher volatility at higher interest rates, we like that one. And then the rates at each node are going to be multiples of e raised to the 2 times the standard deviation. So there's our sigma, and we've talked about sigma in many, many readings. That's our sign for standard deviation. And so that's our signal that we're going to have some kind of volatility in interest rates measured by the standard deviation of interest rates. Of course, that little italicized E is a super important concept in mathematics. It's used in calculus, it's used in all sorts of things, and we're going to use it as well today. Of course, it's related back to the assumption that we're assuming a log normal random walk. right, here's what I was trying to do earlier, do with my hands. I didn't do a very good job because I knew there was a slide coming up. So look at time period 0, that's today. There's the spot rate. Then we go to time period 1 and time period 2. Now, my brain always thinks that my logical first thought is each of those is time period 1 year, time period 2 years, but it doesn't have to be, especially with valuing bonds. So make sure you're sensitive on the exam in the question stem whether the bond is given to you as a semi-annual coupon paying bond or an annual coupon paying bond. If it's annual, it probably simplifies things just a little bit. All right, so let's start with the spot rate, and then what we can do is we can predict what those interest rates are going to be. What is the path? 50% chance that they go this way, 50% chance that they go this way, and then the same 50%, et cetera, et cetera. Notice the one in the middle over there, the I sub 1UD. We reach that point whether we go up and down or down and up. I guess that's the, the associative property of mathematics. Now, the next question is, all right, what are those rates? If this is a random walk, if it's a true random walk, and we start with a spot rate of, let's say, 10%, we could just say, all right, how about next year that the rate is 72%? And then if we go downward, it's 4.2%. I mean, that just doesn't make a whole lot of sense. So what we need is some kind of a framework to estimate and fill in those interest rates for our interest rate tree. And look at the note at the bottom. Those values represent forward interest rates. And this should make perfect sense based on what we talked about in a previous reading about the relationship between spot rates and forward rates and the slope of spot curve and the slope of the forward rate curve. Now, two ways to do this. We can do this based on history, and we talked about this a bunch in level 2 and even probably more back in level 1. The problem with the historical approach is that you're looking back this way into the past and you're saying, all right, if all of the economic conditions hold true from prior to this particular period, then this is a good approach. But as you know, the economy is dynamic and everything out there is dynamic. So it's still a good way to start, but it's probably a little better to use the implied volatility approach. And that leads us to this concept of backward induction. And so when I teach this in my derivative securities class, I always tell my students to pretend. I don't have them do this. I say, pretend what you're doing is you're getting out of your seats and you're going to go back over to the wall and you're going to stand on your head. Let me go back here. So backward induction means that we're not starting in time period 0 and moving our way outward. We're going to start at time period 2 and backwardly induct. I don't really know if that's a term, but we're going to start at the end and move backwards. And that's really all backward induction means. Key points: the value of a bond is known at maturity, right? We're promised a final coupon payment and we're promised a principal payment. So, that's going to be $1,000 or $100, depending on how many zeros you want in your maturity value. And so all you do is you compute the value at each node as the present value of those two possible values in the next period. And then you can use lots and lots of different interest rates. But here, at least initially, we're going to use the forward rate to discount the price at each node. Now remember, we said that there was a 50% chance of going in each direction, and so all we need to do then is use our regular old algebra from 5th grade or 9th grade. That's why we have 0.5 there. That's the 50%. All you're going to do is take half of that value. So let me show you what I have here. 2-year bond, no embedded options. That's important. 8% annual coupons, so we have a spot rate of 4%, and then we've got 9% and 6%. So let's go ahead and work through this backward induction valuation. All right, so what do we know? Step 1, calculate the value of the bond for the up node at year 1. All right, so what do we know? We're getting $100 maturity plus the $8, right? What was the 8% annual coupon? And we're going to discount that at the 9%. Now, in this first step, you don't have to waste your time doing the half of two of those things because they're the same just at that first. But anyway, let's go ahead and work through the mathematics like we're doing it the long way. So that gets us to 99.08. And then we'll do the same thing for the down node. We're going to discount. The only difference here is we're going to discount at the 6%. So look at the middle of the slide. You have 99.08 and 101.89. So those are the two present values at time period 1. Right. And then let's go ahead and just take the present value of those two discounted back at, now watch, this is where it gets just a little tricky. Now we use the 9% once, we use the 6% once, then we're going to use the 4% to get back to the price. And so there's our price, 104.31. And it's probably helpful to look at it here using the interest rate tree. So here's a great summary slide. Notice at time period 2, we start with the 108, right? So that's 108 at time period 2, whether interest rates go way up or way down or whether they go like this. You know the cash flow at time period 2 is going to be $108, $8 of coupon, $100 of principal. So we discount that back to get 99.08 and 101.89. Then we use the $8 in coupon that we get at time period 1 and discount those things back to get the value of the bond, 104.31. So what have we done? We've used forward interest rates to estimate the price of a bond. Now, before I tell you about calibrating, let me go back here to this slide. Notice the spot rate is 4%. Notice the forward rates are 6 and 9%. What did I say earlier? We're assuming some kind of a structured random walk. So we could have put 2% and 11% in there, or 7% and 12% in there. We could do the math here and compute the price. And of course, it'll be different depending on what rates that we choose, 104.31. So that is the present value of the bond. That's the price of the bond using the binomial interest rate tree and forward rates to discount to compute that price of the bond. But now let's move inside of the title of this reading about this arbitrage-free thing, right? So we need to calibrate a binomial interest rate tree. Calibrating, that sounds like a super important word. All right, so what are we going to do? This is what we did in our last reading, right? We looked at the par curve, and then we looked at the spot curve, and then we looked at the forward curve. And of course, we have to compute those based on those par values. Then we're going to take those curves and we're going to construct an interest rate tree. We're not going to just go back here and say, 9 and 6. We're going to construct an interest rate tree using some kind of assumed volatility. And this gets us back to that e raised to the 2 times sigma. Here's a big assumption. What is the standard deviation of interest rates? Is it 5%? Is it 10%? Is it 20%? I mean, with a treasury bond, it's probably not going to be 100%, right? It's not going to be 200%. So we're making some assumptions about volatility, and then we're going to impose that into an interest rate model. We're going to use backward induction to determine the appropriate values at each node, just like we did a minute ago. And then we're going to finally calibrate the tree to ensure it is arbitrage free. Now, the good news for you is that the LOS doesn't ask us to calibrate a binomial tree because that's relatively difficult. And I'll show you why that is here in just a second. However, once we start the calibration process at a starting point, then the rest of it is relatively simple. And hopefully you'll agree with me as we work through the steps. All right, at each node, the forward interest rate can go either up or down. All right, that makes sense. Now look at the second circle point. This is what I was telling you about the starting point. Determine the lower rate iteratively or by solving simultaneous equations. Using known spot and forward rates and then the other features of the bond given its maturity. Now look at these important formulas over there. So what we need to do is start with, here, let me just go back to this tree. We're going to start with, where am I here? We're going to start trying to estimate, all right, we begin with the spot rate, so we can observe that. We know what that is. We're going to estimate what that I is in time period 1 with the lower rate, the D with the lower rate. So here's where we, here, let me repeat this for you just so you get it. Determine the lower rate iteratively or by solving simultaneous equations. So once we determine that rate, then we can easily determine the upper bound because they are functions of all of that stuff we did back in level 1 with confidence intervals and prediction intervals. So notice we have the I at the subscript 1D is raised to the 2 times standard deviation. So those are 2 standard deviations. Remember we looked the numbers up in the Z table or the T table, but they were always around 2. And so that's where we get this. So we're saying 2 standard deviations. So no matter what we pick for that bottom rate, the upper rate is going to be 2 standard deviations away. And of course we need to use the E raised to the X button on our calculator because we're assuming that log normal stuff that we talked about earlier. Let's go ahead and look at a super simple example. I love this first diamond point. An analyst starts the process of calibrating a binomial interest rate model by guessing. All right, the great news for you guys is that the LOS doesn't say, hey, guess what that lower 1-year forward rate is going to be. All it asks you to do is describe the process. Now remember, guessing, it's not really guessing, it's that iterative process or solving simultaneous equations where an analyst can come up with this estimate of the lower 1-year forward rate. So forget about where that comes from. Let's just go ahead and focus on, let's begin at 382. Let's also assume volatility of 20%. And remember, that volatility is not based on just a guess that the analyst develops, but it's based on maybe some history lessons, or maybe it's implied volatility from derivative contracts, or some other kind of a model where an analyst can derive some kind of a volatility assumption. Remember that if we're calibrating a binomial interest rate tree for a treasury bond, we probably are not going to have standard deviations of 70% or 80% or 100%. They're going to be relatively low. All right, so given that 1-year forward rate of 382, all we need to do is use that super simple formula, look under the solution, where 2 standard deviations, just like we did back in confidence intervals and prediction intervals. So all we need to do is take that 382 times E raised to the 2 times sigma, and that gets us 5.7. So think about what we've done here. We have an observed spot rate, and then we're going to estimate that 1-year forward rate of 382, and then we're going to assume our log normal stuff from the very beginning of this slide deck, assume a 20% volatility to work our way up to 5.7%. Now think of those, the actual forward rates that you compute using the par curve and the spot curve. Think of those as kind of averages, and so these things here are kind of a summary of those averages. This is different than the forward rate curve, but it's pretty close to it. Remember, what we're trying to do is to calibrate. Now notice that first arrow point, the arbitrage-free lattice, that binomial tree, and the spot curve are going to lead to the same bond value. This works because this is a fixed rate coupon bond, has no embedded options, and then, of course, this arbitrage free model is going to make certain that those two values are identical. So let's take a look at a little bit more of a complex example. Here we have a spot curve, 1, 2, 3. So there's 4%, 5%, and 6%. And let's go ahead and redo the present value of the bond, the price of the bond, using those spot rates. So if you do that quickly, you get 97.50. Just a quick, make sure you understand this. 5% coupons, right? 3 years, face value of $100. So the math there at the bottom of the slide is nothing really interesting. We did this before. We did it back in level 1. But let's go ahead and let's use this whole arbitrage-free valuation framework. And that's going to be summarized in this interest rate tree. It's binomial because you can have one way or the other. So there's our 4% spot rate. What we've done as a good financial analyst is that we have either use that iterative process, solve for those simultaneous equations, or do I even want to go back here? Where was that slide? Guessing. Do I want to guess? So anyway, however I come up with that 5.123% at time period 1, that's the lower expected forward rate. So then all we need to do is use that equation from the previous page to get us up to 6.886%. Oops, didn't mean to do that. And then we can do the same thing at time period 2 and then work our way up. So notice that at time period 2, 5.899 and 10.693, they're 4 standard deviations away from each other, right? 2 to get to the middle, 7.861, and then 2 more to get up to the 10.69. And then, of course, at time period 3, we have our bond. So here are the bond cash flows, 5 in coupon, 100 in maturity value. And so all we want to do is we're going to use this backward induction to say, all right, whether the interest rate path goes like this, right? Up and up, or down and down, or down up, or up down. We need to compute the present value of that $105 that's received at maturity. And then each time we're going to add the $5 in there. So here's a summary page of all of the mathematics. Feel free to pause the video to work through the math. But what we can do is we can easily start with 105 and divide by, so let me go back here. We have 105 at time period 3. We're going to divide by 1 plus the 10.693%, 1 plus the 7.861%, 1 plus the 5.899, right? Oops, I went the wrong way there. So that's what we have there in the middle of this slide deck. And so notice we get 3 prices, 94,857, 97,348, 99,151. All right, so those are the values at that, whoops. Keep going the wrong way. Those are the values at time period 2. So this backward induction, we're just discounting through time. So to go back to time period 1, all we're going to do is take, here, let me bracket those. Can I bracket the 94 and the 97? And then add, don't forget to add the $5 in coupon. Boy, you know that if this is a multiple choice exam, that one of the answers is going to be without the $5 in there. So make sure you add that $5 coupon that you receive at that time period. And then we're going to discount at the, well, let me go back here, right? So discount both of those at the 6,886. And then at the 5,123, so you get 94,583, 98,218, and then we need to discount those back at the 4%. Don't forget to add the $5 in coupon, and so look at that, $97.50. So note that that was the same number that we got here. So this is, I mean, it's almost like magic. Of course, we went through all the process. We knew that 5,123 was the correctly calibrated interest forward rate at time period 1, and that 5899 was the correct one at time period 2. So what we've done is we have calibrated the binomial interest rate tree to produce an arbitrage-free value consistent with the spot rate curve. I would memorize that second to last diamond point to reinforce what that LOS is trying to get us to do. So feel free to pause and go back and do the math yourself so that you can convince yourselves that the math is in fact correct. And then of course, the LOS asks you to calculate, so you need to make sure you can do this on the exam. Now, I will offer some private editorialization here. If the CFA Institute gives you the 1,000-year bond that I've talked about in previous recordings, just pick B and move on with your life. 1,000 interest rate nodes out there, you could probably spend the next month working on that and you still never get an answer. So my point is, expect a 3-year bond, maybe a 4-year bond. It's tough to go out to 5 years and beyond just because of the limits of time. So let's take a deep breath and remind ourselves what we did. We calibrated the binomial tree because 9750 ended up equaling 9750. Now, the calibration relies on the accurate arrival at that 5.123%. If in fact, and the reading does make this suggestion, if in fact you chose 5.132% and then did all the math and then did all the present value, and the present value here came out to be 96 or 99, you knew that you have incorrectly calibrated, and so then you must recalibrate and then recalibrate and recalibrate. But you can envision, even an Excel spreadsheet can do this relatively quickly, where you can write a macro and say, okay, if this thing works here, then we're done. If it doesn't work, then add a little bit to it. And you can see all those results, and you'll see you're getting closer and closer and closer and closer to the actual price. All right, moving on to something else, right? So here's this pathwise valuation. And it's very similar, but it's not nearly as complex as backward induction can be. So here are some steps here. Come up with a list of all the possible interest rate paths. All right, that should be okay. Discount the cash flows and determine the average. So let me give you an example here. Using our same forward rates, right? We call those implied forward rates. That interest rate tree that we just did, what we can do is say the following. The interest rate path, we can go from 4% to 688 to 1069. We can go 4 to 688 and then down to 781. We can go 4 to 513, then up to 786. We can do 4, then 51, and then to 58. So those are the 4 possible paths, and this sounds like a pretty good exam question. Go ahead and compute those present values, and I'll show you that in the next slide. But there are the present values over there, 94, 96, 98, and 100. And then you just take the average of those. So let me make sure you understand how we compute that. Well, let's do the 94. Let's do the 9464 and the 9688, and then we'll skip the last 2 steps. You can confirm those yourself. So for present value for path 1, we're going to discount the first 5% at 4%, right? Then we're going to discount the second $5. Did I say 5%? We're going to discount the first $5 at 4%. Discount the second $5 at 4%, then the 688, right? And then the third $5 and the last par value of $100 at 4%, 688, and 10.693. So that's how we get the 94.96. And if you do the same thing, you can get 96.88, and you can get the 98.42 and the 100.07. So feel free to pause the video, make sure you can do all of that math. But then for those of you who trust us in the math, then go ahead and just take the average. So since we have the 4 paths, just divide those by 4. And there's the 9750, which we're not surprised. Where am I back here? We're not surprised that we got that 9750 because we used a calibrated implied forward rate tree. And then the last LOS asks us to be reminded that Monte Carlo simulation is relevant for lots and lots of stuff that we do in the CFA program. So of course you can do Monte Carlo simulations here for interest rate trees. This is kind of like what I was hinting at just a moment ago when I reminded you of how valuable Excel is. But what you do is you just run this computer algorithm over and over again to calibrate those paths to ensure an arbitrage-free valuation. Now, sometimes there is not the possibility when you do all of this, because you have so many of these paths and so many of these distributions and assumed volatilities, so that you can add a drift parameter. Look at that third circle point. A drift parameter to all the interest rates to ensure that the Monte Carlo model is arbitrage free. So think about going back and putting together that interest rate tree and adding a constant, a drift parameter to each one. I mean, you get a migraine thinking about all this. So it makes perfect sense then to use Monte Carlo. And the reading has a nice, really clear written paragraph about why mortgage-backed securities are usually and specifically applying this Monte Carlo forward rate simulation. Now, if I really like those term structure models, those term structure theories, I like these term structure models as well. So what we're trying to do here is we're trying to predict some future interest rate. So what I want you to do, I'm going to scroll through these quickly. Look at the DR to the left-hand side of the equal sign. This is a small change in the interest rate. And it's probably a small change in a short-term interest rate. Now, this is the Vasicek model. So I'm just going to scroll through these kind of quickly here. Here's the CIR model. We'll talk about this in a second, but notice to the left of the equal sign, there's the DR. And here's the arbitrage-free model, the Ho-Lee model. There's the DR. So to the left of the equal sign, what we're doing in each one of these models is that we're trying to predict a small change, D stands for change, a change in an interest rate using a handful of models. All right, so describe modern term structure models. All we're doing is trying to predict an interest rate at some time in the future. All right, so what are we going to base our estimate on? Well, we're going to base our estimate on a couple of things. Change in time, right? Look at the DT, small increment of time. 1 day, 1 minute, right? Maybe 1 week. So a small increment of time, which is deterministic because we know how long of a time period that we want to measure. But what we're also going to do is we're going to have a plus sign there. So notice there's a plus sign, and we're going to allow changes to randomly occur to that interest rate. Think of it as maybe random walking up or random walking down or random jumping or random something or other in there. But notice there's that lowercase sigma in there. So that stands for standard deviation like it always does. So what we're doing is we're adding some kind of a risk element to this model. Now, one of the things that we know, and we learned this back in our quantitative methods days, that there are patterns in variables that are observed and can be used. And one of those patterns is this reversion to the mean. And so this is what we know in interest rates, is that if interest rates are super high, they're never going to go super, super, super high. I shouldn't say that, but they're probably not going to continue to go super, super. They're going to fall back to some mean level or some moderate or average level, right? Because what are interest rates essentially? Interest rates essentially, from a pure economic standpoint, are really a trade-off between consumption today and consumption tomorrow. So that's based on the productivity and the individual tastes of the consumers. So when economies grow, if they grow like this, maybe the economy grows like this, let's say that's 5%, interest rates can't be 1,000%, right? They're going to sometime revert somehow over some time period revert to the mean. So this is all I want you to do before I get to the next slide is look at this Vasicek model. So we're looking at the change in interest rates. We have a deterministic part and a stochastic part. And here's a good old slide that determines, that shows you what all those variables mean. So the alpha determines the speed, let me do my little running there, the speed of the mean reversion. A high alpha implies fast reversion. So a high alpha might say something like, oh, if interest rates spike up, they're going to quickly come back down. Mu is exactly what you might think it is. It's the mean level of that short-term rate. dr is the infinitely small increment in the short-term interest rate. What did I say just a slide deck ago? Maybe an hour, maybe a minute, maybe a day, probably not 1,000 years. So infinitely small increment, I don't even know what that means, right? You have to get a microscope out and look at the atom. Infinitely small. dt, infinitely small increment in time. So when I blink my eyes, that's too long to be infinitely small. So there's standard deviation, that's volatility. And look at dw is the stochastic process that models the risk. So what we're going to do is we're going to allow standard deviation to get into the model. And it's going to influence this stochastic process. Think of it maybe as a random walk that we're going to go up and down. And if we're going way up and way down, that's going to be reflected in that lowercase sigma. Look at that final arrow point model allows the yield curve to be upward sloping, downward sloping, or humped based on those selected parameter values. All right, so here's this Vasicek model. And look at that top diamond point. And this is probably a good answer here on the exam. Permits interest rates to be negative. Some people think that's a drawback of the Vasicek model, but you guys know that in the last decades or so, we have had negative interest rates for more than just short time periods in multiple countries throughout the world. Now, what the Cox-Ingersoll-Ross model does is the exact same thing, very, very similar, but notice over there on the far right, there is a square root of R, a volatility coefficient. What this does is that it guarantees, look at the teardrop point, guarantees that interest rates will remain strictly positive. But what it also does is that enables an increase in interest rate volatility when interest rates rise, right? If interest rates are 1%, what are they going to do? They're going to go to 1.04% and then 1.01% and then 0.99%. So what's that volatility? Whatever that is. But if interest rates are 10%, they might go jump to 11% or 12%. So you have the same percentage, jumps, but what we know is that at higher interest rates, there's more standard deviation. So the CIR model enables us to incorporate what we know about interest rate volatility into the model to be able to predict changes in interest rate. So look at the bottom there. In contrast, Vasicek model assumes that interest rate volatility is constant. So that's a big difference between those two models. But notice they have everything else that is identical. Now let's get back to this concept of arbitrage-free models. All we're trying to do is use some kind of a theoretical model that uses actual stuff, right? Actual variables. Let's call it, in this case, a yield curve, so that we can estimate those future interest rates. Arbitrage-free, of course, means that there are no arbitrage opportunities out there. And so here's an arbitrage-free model, the Ho-Lee model, where we're adding theta is just a drift parameter. So all we're doing is saying that over this small increment of time, we're allowing the interest rate to drift. Drifting can be upwards, drifting can be downwards, and then we're going to add that stochastic component as well. Notice the Ho-Lee model does not have that square root of R in it. And I think that takes us through the LOSs. Let me just repeat what I said earlier so that now that we've been through this slide deck, this should make perfect sense. I think that second LOS is super important. Calculate the arbitrage-free value, right? If you can do that, well, then you can do LOS 3, LOS 4, LOS 5. You understand LOS 6 there, and then all of that tells you about arbitrage-free valuation. And then the pathwise valuation, I think that's pretty simple. So you ought to be able to go over that one time and then answer that question correctly on the exam. And then Monte Carlo, just use all of your knowledge of Monte Carlo simulations to be able to answer that.